So up next, talking to us about modeling the active and idle durations of network hosts, we've got, now I'm going to try not to butcher this time, Soumyo Moitra? That's close enough. Soumyo is a senior member of the technical staff with the Network Situational Awareness Group at CERT SEI. Thank you, Soumyo.
Well, it's still good morning, and I'm Soumyo Moitra, and I'm just going to talk about one particular aspect of flow data that I was looking at, that I analyzed, and that is the activity and the idleness patterns. And while you're looking into this, I can also say that it's basically a conceptual presentation, and I'm not going to go too much into mathematical or technical details at this stage. So for a variety of reasons, for this audience, it's fairly obvious that we need to understand the network behavior of hosts for a variety of reasons. And one aspect of the behavior of hosts is the duration during which they're active and when they're idle, and what the exact pattern is of activity and idleness. And of course, this has to be done by host type. Again, that is obvious to all of you over here. These patterns of activity and idleness are, one, important for situational awareness. We need to track whether the patterns are similar or whether they're changing significantly. We can baseline them and look for anomalies. And of course, anomalies always need to be investigated further. There's also a particular motivation for this analysis, and that is we were interested in deciding how we can support the inventory within a network that we're interested in. And if a host is always active and we see it on the traffic flow, then we know it's active. But of course, hosts are sometimes idle. And sometimes they can be idle for quite a long time. So the issue arises whether, in fact, they still are active or not, even though we haven't seen them for a while. So this is where we need to analyze the distribution of the idle times and try to make some decisions on whether it really belongs in the inventory or whether it's actually been taken off or dropped or whatever. And there might be other implications and repercussions of this. If IP address has not been seen for a long time on the traffic data, then there may be other issues involved. Any number of things. There may be some malicious activity involved, or it may be the precursor of some malicious activity. So there's a number of reasons why we need to understand this and see and keep track of the active inventory of hosts. And in fact, this is one of the top controls in many of these lists that you see of security controls for network managers. The active inventory is one of those controls. So as I've basically mentioned already, the objective is to look at the durations and the distribution of the durations of these active and idle times. One, they can give insights into different behaviors, and we'll look at that when we look at some of the data. And also, we can derive two metrics from them. One would be the probability of a host being active after a certain period of idleness. We can make some judgment according to that if we know the distribution. And in reliability, if you think of that, it's called the survivability function. Another metric is the conditional probability of a host being active within a time horizon, and we have seen that it has been idle for a certain length of time. So it's conditional on it being idle for some time, and then we want to know whether it'll ever come up again, will we ever see it again. And this is actually, in reliability theory, what's called the conditional survivability function. So there are parallels, and a lot of work has been done in reliability theory using these two metrics. What I'm doing over here is simply applying those metrics to looking at activity and idle times. The data is in the public domain. In fact, it's the same data that Lee talked about. I've basically used Silk and some Unix tools and spreadsheets. So I haven't actually used any statistical package to do this analysis, but of course, using a statistical package may make things much easier, and we would be able to do a lot more things much easily. Now, the focus here is on web servers. As I mentioned, it's important to isolate the server type, the host type. And in this case, the hosts are going to be the web servers, because each kind of host will have a different pattern in this activity and idle times. So it's very important to segment that in some way. And given that you take a homogeneous set of hosts, the methodology is applicable to any type, but you have to look at the same type at a time. What I'm discussing has been written about in many places. There are a whole bunch of references. This is just a small subset of the references in statistics, stochastic processes, renewal theory, and so on. So I just put a few down, and everything that I'm saying is actually somewhere in this literature. So about the analysis, we're looking at out traffic, because if we are interested in looking at activity, then it's the out traffic that is relevant over here. In traffic may or may not indicate activity. So out traffic, because of the data set I'm looking at, and I was particularly interested in having a public domain data set so I could present it. The longest time horizon I could find in this data set was 23 hours. Now, that is a limitation. I would have preferred a much longer time window, but I was limited by the data. And it's continuous time. So the data is over a number of days, but in fact, there are gaps in that data. So the longest continuous time window I could find was 23 hours. The time scale or bin size, for those of you who do Silk, is 1 hour. So the analysis goes in the following steps. We look at the volumes that we observe in each hour, in each bin. And if there is any activity, if we see any traffic in it, we code it as 1. And if there's no traffic, then it's 0. And from that 0 ones, we can compute the durations of active times and idle times. So active times are the sequence of ones, and idle times are the sequences of zeros. And we plot the distribution function. This is the analysis that I'm going to be talking about. This is an example, completely hypothetical example to show how we get those activity times, which are denoted by T's, and the idle times denoted by U's. So we just count them, okay? And you can see that over here, the volumes themselves don't matter as such. It's whether we observe any traffic at all in that time window. And this is the result. So what we have here are two distributions. One is the distribution for the active times, and one for the idle times. And let's look at this distribution a little bit. When we look at the active durations, we basically see that this is, remember, this is being continuously active. So we see that they're continuously active at most for 5 hours. You don't see anything after that. So that's sort of significant. For these set of servers, the activity is very sharply delineated, and one, of course, can fit a distribution to that. With such a small data set, fitting would be not very meaningful. But what we do see is that there's a cutoff. And we can get the basic statistics, the means and the variances and all that from that. But what I want to emphasize is that it's a very compact distribution. At most, they're active for 5 hours, and then nothing happens. Now, in other data sets, you will get a different distribution. But if you do see this pattern that activity is sharply limited and after a while there's no activity, and then suddenly as you keep monitoring your system, you suddenly see a server being active for a much longer time, that's an anomaly. And that certainly requires additional attention. So that's the main advantage of looking at the distribution of the active durations. Okay? Now, for the duration of the idle times, it's a little more interesting. So you see that it's quite common for these web servers to be idle for up to 7 hours. Although the sample size is small, but it's clearly possible that under normal circumstances, they would be idle up to 7 hours. Then there's an interesting gap. And basically, we have, you would think that there are basically two populations, and probably that is the case. So then there are some servers that start being active again after a long period of time. Now, because of the cutoff of 23 hours, I can't go beyond that, but this suggests that there are some routine activities that start up around 24 hours. So a few hours before the 24-hour cycle and a few hours after the 24-hour cycle, that would explain those numbers over there. So there's some routine activity that is going on, and the servers start up again and have some traffic, and then between 7 hours and roughly 17 hours, these servers in this particular data set seem to be idle. They just don't do anything in this time. So this is also interesting. And again, this suggests a number of things. One, of course, is that it's also useful to detect anomalies. If you suddenly see some servers in between where normally they should be idle, then again, that's cause for an alert. But also what you see is that you need to disaggregate the servers by their behavior. This is clearly a behavioral issue. And you need to look at the distributions by type of servers, and then you can compute those metrics. I'm actually not going to discuss those metrics per se, and the reason I can't estimate those two metrics with this data set is because the sample size is just too small. It wouldn't be sensible. But it shows how you can estimate those two metrics. So for the population of servers that are idle between 1 and 7 hours, if they're idle for a longer time, that may be okay, and you have to see what happens afterwards, whether they start up again. And from that, you can actually get those metrics and make a decision whether the server is actually out of service or not from that distribution. But if you look at the idle time distribution, there's something, again, because the sample size is so small, I can't be sure, but it does look as if there are two overlapping distributions. That part seems to be bimodal. So maybe within those servers that are active for short periods of time, there are two behaviors involved. And if you have more sample size, if you have a bigger sample size and you have more servers to look at, you could investigate that. You could, in fact, separate the servers by their behavior on this. And perhaps that will give you some additional insights as well as to what's going on. Any questions? So this is basically my results. As I say, you need these distributions for getting those metrics. Yeah.
I'm trying to remember the details of the collection of the LBNL data, but I think there's a very good explanation for what you've done, if I remember correctly, and that is that not all networks or subnets in LBNL were collected simultaneously, and the taps moved around to capture different address spaces, which of course would make the servers in address spaces that weren't being monitored appear
except
to be
that this is the same time window.
It doesn't matter. I mean, within that same time window of 23 hours.
If we've done that, yeah.
Was everything collected continuously during that time window?
Yeah,
I don't.
We don't know.
I don't remember from the paper whether there is a table that says what subnets were collected for what durations. But my gut feeling is that you're seeing an artifact of the collection rather than a behavior of the servers.
No, that wouldn't happen because it will show up in the distributions. You wouldn't get this kind of a separation.
Hey, John, I did have an opportunity to look at the LBNL data set recently, and the movement, there were sensors that moved, but they moved on a much larger time scale than what you're referring to.
Okay, I wasn't sure, but it's buried in one of their papers and it's on the book. Thank you, Tim.
Yeah, as I said, that would confirm the kind of patterns we see. So just a couple of points. I've mentioned most of them. The active durations are very compact. They seem to be narrower than a Poisson, and in reliability theory, they use the Weibull a lot. Maybe that's a better one. In terms of idle durations, it's very important to realize that they're censoring and truncation issues. And we really need much longer time periods, which is the future work, and the others. Yeah, go ahead.
So I wanted to just, and forgive me if I'm stating the obvious here, but I wanted to talk for a minute about the relationship between a host that's active and a host that's connected and online. And the difference between those two is probably going to depend on how close to the host you're actually collecting the data. Given the characteristics of modern operating systems, if you're in the same broadcast domain, if it's online, it's emitting traffic constantly. If you're collecting a hop or two away, you'll still probably see some administrative stuff like NTP.
What you're saying is that we might have sensors somewhere else, and that would pick up some traffic. The assumption here is that these sensors are picking up whatever traffic the web servers might be.
And the reason that I wanted to point that out right now is because it actually links back to the previous presentation, and that is that if what you see depends on where you collect, then maybe repetition is not such an evil thing after all, as long as you interpret it correctly.
Yeah, that's always true. The issue of placing sensors is an open issue. And as I say, so longer time periods, and we need some more metrics with more data sets and so on. And there are a number of biases. And there are actually methods to correct for those biases. I didn't go into that, but in the reliability theory literature, that's covered. And also the coverage of sensors is also discussed in the literature. It goes without saying that different host types will have different patterns. And another issue, which actually is rather important, is that varying the time scale, the time windows, and the time horizons can actually provide a lot more insights. I was limited with this particular data set, and hour seemed to be the most reasonable time scale for this analysis. But it should be varied, and it's quite surprising how varying the time scale and looking at the time scale over different time windows can be different. The time horizon, what I talk about, is the overall time that is possible for you to do the analysis. So that's basically what I have for future work.